Hey everybody, today we're going to talk about serviceability. Um, I only have time to cover general deflection criteria today, so we're not going to cover seismic deflections, crane or skylight deflections, thermal expansion, vibration. Let's get right into it. So design guide number 3 from AISC is an easy read, and it's the authority on deflection. But the tables don't provide context for their criteria. So you really want to read the manual. There's more to it than just the tables. So roofing joints are not building joints. So don't mistake that. Yes, you have to put joints in the roofing materials, but you don't necessarily have to put joints in the entire building. Understanding the table columns, what the type is, the structural element, deformation, recommendation. This is what they're recommending, and then the loading criteria. So where do these recommendations come from? Well, they come from experience. If it ain't broke, don't fix it. They didn't necessarily do a lot of testing to say, hey, this is when you start to see cracks. It's just historical. This has always worked. Take note of the loading conditions here. So they're very odd sometimes. So look at this purlin, you're dead plus half snow, which is unreasonable. Then there's this dead plus 5 PSF. So the loading conditions really matter. For cladding, the Metal Building Systems Manual does a better job of capturing the commentary. So here's the Metal Building Systems Manual. The two are very, very similar, except they have in the Metal Building Systems Manual these little symbols, right? So in this particular one, it says 1/16 of the crack width, but down below there, you'll see it says, hey, you can get up to 1/8 of an inch with proper detailing. And then this symbol here it says you can go as low as H/100. But if you look at the table on the right for serviceability from AISC, it doesn't have these things. But if you read the commentary, it is in there. It's just not noted very well in the tables. So then this one here, again, depends upon window head details, and then this symbol here for cladding weight. Rotation on masonry lintels is also limited. So this is something that is often overlooked, especially because rotation in most programs is, enter calc or whatever. It just doesn't check rotation, but they are limited to a 1 degree maximum. So here's an example of a weird job that I had in the past. No, I don't recommend doing this, but it solved the issue of the day. So there is this rotation way out there. So that's why that tube, that lintel tube there in the middle is very large, is because I had to limit the rotation on that lintel. Metal connectors. There's nothing in this table about metal connectors. But, in reality, you don't want if you have, like, this is a metal stud with a concrete floor, steel beams, you can bottom out that connector very quickly if you don't pay attention. So most connectors have like a 3/4 inch deflection criteria, and if you allow greater than that, you're bottoming them out. And you also have to, this pretty much. So here's the space that's allowed. You got to account for that, and you have to account for the order of the concrete pour. So, if this is a concrete plank, or and it has a topping above, and they put the stud in, they put the topping down 2 or 3 inch topping on the concrete plank, and you'll bottom that clip out real quick. So the other thing to pay attention to is the loading conditions are the 10-year wind as opposed to the 50-year wind that we use for all our design calculations. So if you read the book here, it says, in lieu of using the precision of a map with a 10-year wind speed isobar, the authors recommend using 75% of the 50-year pressure as a reasonable plus or minus 5% approximation of the 10-year wind pressures. The commentary to Appendix B of AISC 702 recommends 70%. So the current design guide refers to AISC 702, and of course there's newer versions now. So if we go to that AISC 702, there's that 0.7 factor, all right? And this is the wind chart. You can see that it's 90 miles an hour. But what about AISC 710? So this is the first iteration where it starts to change, right? And if you read there, for applications of serviceability design using maximum likely events or other applications, it may be desired to use wind speeds associated with mean reoccurrence intervals other than those given in these figures. And Appendix C. So they refer you to Appendix C. So you go to Appendix C, and this is what you'll find. And it's important, I think, to read this. The use of nominal 700-year mean reoccurrence intervals. Wind load in checking serviceability is excessively conservative. The following load combination in these equations can be used to check short-term effects. So here's that equation, dead plus half-live plus WA, in which WA is a wind load based on serviceability winds. Some designers have used a 10-year MRI for checking the drift under loads for typical buildings, whereas others have used a 50-year MRI or a 100-year MRI for more sensitive, drift-sensitive buildings. The section of MRI for serviceability evaluation is a matter of engineering judgment that should be exercised in consultation with the building client. Notice the term engineering judgment, right? This is not codified. There are some things, of course, but there's a lot of engineering judgment into which, are going to use 10-year wind or 50-year wind. The maps included in this appendix are appropriate use with serviceability limit states and should not be used for strength limit states, ASD versus LRFD. So they're switching design methodology, so you got to pay attention. Because of its transient nature, wind should not be considered in analyzing the effects of creep or other long-term actions. So this is the figure in the commentary, and then you compare to the wind in the regular map, so 115 versus 76. And this is the older codes. You can see the vast majority was 90. So let's just focus on the field there, 90, 115, and 76. So let's just run some quick numbers, AISC 702. So there's the formula for your wind pressure, right? And so we take a 10-year over a 50-year, and these values are the same, so we can just cross those off. So we get 76 squared over 90 squared, and that ratio is 0.71. And that's right where the design guide 3 says we want to be. We want to be between 0.7 and 0.75 to get to the 10-year wind, all right? But now let's do it with AISC 710. So now, same formulas, okay, 76 over 115, but we get 0.44, but we're really expecting 0.7 to 0.75. So what's going on here? So there's that formula, WA, and WA is based on serviceability winds, right? So it's a conversion thing. So if we look at the old tables, we go from 90 to 115, right? What were we doing? We were multiplying by this factor. We were converting from ASD to LRFD, so that radical one of 1.6. So we converted to ASD. So here's the same calculation, but this time we put in that 0.6 and we converted down. And this gets us right where we want to be, right? So now we're at 0.73. We want to be between 0.7 and 0.75. Bada boom, bada bing, and we're 0.73. So the ratio is correct. Now, this, of course, is depending upon how you put your combinations into a given program. Are you doing ASD or are you doing LRFD? So if your case is this and you're doing that 0.6 wind, which means you're doing an ASD, we're multiplying by 0.7 to 0.75. If your case is L or FD, then we're going to multiply by that ratio, and the example we just did was 0.44. All right. So now let's fast forward to AISC 722, and look, they're playing games with us on these charts again. But the one on the right is AISC, the chart on the left is LRFD. So any questions here?